Einstein and the Story of Lumen, the avatar of beyond light. Conversation held during April 1920 destroyed an illusion which had become dear to me. It concerned the fantastic figure, Lumen, conceived as an actual human being, imagined as endowed with an extraordinary power of motion and keenness of sight. Mr. Lumen is supposed to be the invention of the astronomer Flammarion, who produced him in the retort of fancy, as Faust produced Homunculus, to use him to prove the possibility of very remarkable happenings, in particular, the reversal of time. Einstein declared outright, firstly, Lumen is not due to Flammarion, who has derived him from other sources, and secondly, Lumen can in no way be used as a means of proving things. Moskowski. It is at least very interesting to operate with him. Lumen is supposed to have a velocity greater than that of light. Let us assume this as given, then the rest follows quite logically. If, for example, he leaves the Earth on the day of a great event, such as the Battle of Waterloo, and— may I trace out this example, at the risk of tiring you? Einstein. Do repeat it, and act as if you were telling something entirely new. It is clear that the Lumen story gives you great amusement, so please talk quite freely. But I cannot forgo the privilege of showing later how the whole adventure and its consequences must be demolished. Moskowski. Well then, the person, Lumen, sets off at the end of the battles of Waterloo to make an excursion into space with a speed of 250,000 miles per second. He thus catches up all the light rays that left the field of battle and moved in his direction. After an hour, he will already have attained a lead of about 20 minutes. This lead will be gradually increased so that at the end of the second day, he will no longer be seeing the end of the battle, but the beginning. What has Lumen been seeing in the meantime? Clearly, he has been observing events happening in the reverse direction, as in the case of a cinematograph which is exhibiting pictures backwards. He saw the projectiles leaving the objects they had struck and returning into the mouths of the cannon. He saw the dead come to life, arise, and arrange themselves into battalion order. He would thus arrive at an exactly opposite view of the passing of time, for what he observes is as much his experience as what we observe is ours. If he had seen all the battles of history and, in fact, all events happening in the reverse order, then in his mind. Before and after would be interchanged. That is, he would experience time backwards. What are causes to us would be effects to him, and our effects would be his causes. Antecedents and consequence would change places, and he would arrive at a causality diametrically opposite to our own. He would be quite as justified in adopting his view of the happening of things according to his experiences and of the causal nexus as it appears to him, as we are justified in adopting ours. Einstein. And the whole story is mere humbug, absurd, and based on false premises, leading to entirely false conclusions. Moskowski. But it is only to be taken as an imaginary experiment that plays with fantastic impossibilities to direct our ideas onto the relativity of time by a striking illustration. Did not Henri Poincaré adduce this extreme example to discuss the reversal of time? Einstein. You may rest assured that Poincaré, even if he used this example as an entertaining digression in his lectures, took the same view of Lumen as I do. It is not an imaginary experiment. It is a farce, or, to express it more bluntly, it is a mere swindle. These experiences and topsy-turvy perceptions have just as little to do with the relativity of time, such as it is taught by the new mechanics, as have the personal sensations of a man, to whom time seems long or short according as he experiences pain or pleasure, amusement or boredom. For in this case, at least the subjective sensation is a reality, whereas Lumen cannot have reality because his existence is based on nonsense. Lumen is to have a speed greater than that of light. This is not only an impossible, but a foolish assumption, because the theory of relativity has shown that the velocity of light cannot be exceeded. However great the accelerating force may be, and for however long it may act, it cannot cause this limit to be transcended. Lumen is supposed to be equipped with the organ of sight, that is, he is supposed to have a corporal existence. But the mass of a body becomes infinitely great when it reaches the velocity of light, so that it is quite absurd to go beyond this stage. It is admissible to operate with impossibilities in imagination, that is, with things that contradict our practical experience, but not with absolute nonsense. That is why the other adventure of Luhmann, in which he jumps to the moon, is also an absurdity. In this, he's supposed to leap with a speed greater than light, and when he reaches the moon, to turn round instantaneously, with the result that he sees himself jumping from the moon to the earth backwards. This jump is logically meaningless, and if we try to make deductions of an optical nature from such a nonsensical assumption, we deceive ourselves. Moskowski. Nevertheless, I should claim extenuating circumstances for this case on the ground that I am enlisting the help of the conception of impossibility. A journey even at a speed of only 1,000 miles per second is impossible for a man or a homunculus. Einstein. Yes, according to our experience, if we measure it against facts. We cannot state definitely that a journey into the universe at an enormous yet limited velocity is absolutely impossible. Within the indicated bounds, every play of thought that is argued correctly is allowable. Moskowski. Now, suppose that I strip Luhmann of all bodily organs and take him as being a pure creature of thought, entirely without substance. A velocity greater than that of light can be imagined, even if it cannot be realized physically. If, for example, we think of a lighthouse with a revolving light and consider a beam of light about 600 miles long, which rotates 200 times per second, then we could represent to ourselves that the light at the circumference of this beam travels with a speed of nearly 760,000 miles per second. Einstein. As for that, I can give you a much better example of the same thing. We need only imagine that the Earth is poised in space, motionless and non-rotating. This is physically admissible. Then the most distant stars, as judged by us, would describe their paths with almost unlimited velocities. But this projects us right out of the world of reality into a pure fiction of thought, which, if followed to its conclusion, leads to the most degenerate form of imagination, namely to pathological individualism. It is in these realms of thought that such perversities as the reversal of time and causality occur. Moskowski. Dreams, too, are confined to the individual. Reality constrains all human beings to exist in one and the same world, whereas, in dreams, each one has his own world with a different kind of causality. Nevertheless, dreams are a positive experience and signify a reality for the dreamer. Even for waking reality, it would be easy to construct cases in which the causal relationship is shattered. Suppose a person who has grown up in a confined retreat, such as Caspar Hauser, looks in a mirror for the first time in his life. As he knows nothing of the phenomena of optical reflection, he sees in it a new, objective world that gives a shock to, or even subverts, his own idea of causality, insofar as it may have become developed in him. Luhmann sees himself jump backwards, whereas Caspar Hauser sees himself performing gestures on the wrong side of his body. Should it not be possible to draw a reasonable parallel between these two cases? Einstein. Quite impossible. However you set about it, your Luhmann will inevitably come to grief on the conception of time. Time, denoted in physical expressions by the symbol t, may indeed be given a negative value in these equations, so that an event may be calculated in the reverse direction. But then we are dealing with pure matters of calculation, and in this case we must not allow ourselves to be drawn into the erroneous belief that time itself may travel negatively, that is, retrogressively. This is the root of the misapprehension, that what is allowable and indeed necessary in calculations is confused with what may be thought possible in reality. Whoever seeks to derive new knowledge from the excursions of a creature like Lumen into space confuses the time of an experience with the time of the objective event. But the former can have a definite meaning only if it is founded on a proper causal relation of space and time. In the above imaginary experiment, the order of the experiences in time is the reverse of that of the events. And as far as causality is concerned, it is a scientific conception that relates only to events ordered in space and time, and not to experiences. In brief, the experiments with Lumen are swindles. Moskowski. I must resign myself to giving up these illusions. I must frankly confess that I do so with a certain sadness, for such bold flights of constructive fancy exert a powerful attraction on me. At one time, I was near outdoing Lumen by assuming a superlumen who was to traverse all worlds at once with infinite velocity. He would then be in a position to take a survey of the whole of universal history at a single glance. From the nearest star, Alpha Centauri, he would see the Earth as it was 4 years ago, from the pole star as it was 40 years ago, and from the boundary of the Milky Way as it was 4,000 years ago. At the same moment, he could choose a point of observation that would enable him to see the First Crusade, the Siege of Troy, the Flood, and also the events of the present day simultaneously. Einstein. And this flight of thought, which, by the way, has been indulged in repeatedly by others too, has much more sense in it than the former one, because you may make an abstraction which disregards speed altogether. It is only a limiting case of reflection. Moskowski. I should like to touch on other limiting cases, in particular two that I find it impossible to interpret. Lotz mentions them in his Logic. The first concerns the infinitely long lever whose fulcrum, or turning point, is at the confines of the universe. According to the laws of levers, a mass of magnitude 0 will suffice to keep in equilibrium at the end of the other lever arm any weight, no matter whether it is 1,000,000 times heavier than the Earth. Our imaginations cannot even picture this, yet I cannot feel satisfied with the mere explanation that it is an exceptional case, an extension of a general law to a case in which it is no longer applicable. The second example is still more perplexing because it does not require a journey into other worlds, but leads us into inconceivable consequences, even if we remain on the Earth. Lotz considers this second limiting case easier. To me, it seems more difficult. It is this. The force that a wedge exerts is inversely proportional to its thickness. If it is infinitely thin, this formula gives an infinitely great result, whereas, actually, the force exerted is nil. This very thin wedge, transformed finally into a geometrical plane, should be able to split in twain any wooden or even steel block. And now, consider a special arrangement of this wedge, in which it is resting with its extremely sharp edge vertically downwards, whereas at the top it broadens to a little ledge which supports a weight. We then get the incredible result that this wedge, which can be imagined concretely, should be able to cut through the whole Earth with its extremely fine edge if placed on some base. Where is the fallacy in this case? Einstein. The mechanical facts have not been taken sufficiently into consideration. He illustrated his further remarks by drawing a few strokes with his pen, and proved from his diagram that a wedge of this sort would be able to perform what I assumed, only if the base on which it is placed is composed of separate laminae. Otherwise, the assumption that the force is infinitely great would be erroneous. The final result stated by Einstein was, the universe, both as regards extent and mass, has finite limits and can be measured. If anyone asks whether this can be pictured, I shall not deprive him of the hope. All that is required is a power of imagination that is great enough to follow a pictorial description and that can take up the right attitude towards a sort of figurative representation.
Albert Einstein, in his own words on religion and science. Part 1. Everything that the human race has done and thought is concerned with the satisfaction of deeply felt needs and the assuagement of pain. One has to keep this constantly in mind if one wishes to understand spiritual movements and their development. Feeling and longing are the motive force behind all human endeavor and human creation, in however exalted a guise the latter may present themselves to us. Now, what are the feelings and needs that have led men to religious thought and belief in the widest sense of the words? A little consideration will suffice to show us that the most varying emotions preside over the birth of religious thought and experience. With primitive man, it is above all fear that evokes religious notions, fear of hunger, wild beasts, sickness, death. Since at this stage of existence understanding of causal connections is usually poorly developed, the human mind creates illusory beings more or less analogous to itself on whose wills and actions these fearful happenings depend. Thus one tries to secure the favor of these beings by carrying out actions and offering sacrifices, which, according to the tradition handed down from generation to generation, propitiate them or make them well disposed toward a mortal. In this sense, I am speaking of a religion of fear. This, though not created, is in an important degree stabilized by the formation of a special priestly caste which sets itself up as a mediator between the people and the beings they fear, and erects a hegemony on this basis. In many cases, a leader or ruler, or a privileged class whose position rests on other factors, combines priestly functions with its secular authority in order to make the latter more secure. Or the political rulers and the priestly caste make common cause in their own interests. The social impulses are another source of the crystallization of religion. Fathers and mothers, and the leaders of larger human communities, are mortal and fallible. The desire for guidance, love, and support prompts men to form the social or moral conception of God. This is the God of providence, who protects, disposes, rewards, and punishes. The God who, according to the limits of the believer's outlook, loves and cherishes the life of the tribe, or of the human race, or life itself, the comforter in sorrow and unsatisfied longing, he who preserves the souls of the dead. This is the social or moral conception of God. The Jewish scriptures admirably illustrate the development from the religion of fear to moral religion, a development continued in the New Testament. The religions of all civilized peoples, especially the peoples of the Orient, are primarily moral religions. The development from a religion of fear to moral religion is a great step in people's lives. And yet, that primitive religions are based entirely on fear, and the religions of civilized peoples purely on morality, is a prejudice against which we must be on our guard. The truth is that all religions are a varying blend of both types, with this differentiation, that on the higher levels of social life, the religion of morality predominates. Common to all these types is the anthropomorphic character of their conception of God. In general, only individuals of exceptional endowments and exceptionally high-minded communities rise to any considerable extent above this level. But there is a third stage of religious experience which belongs to all of them, even though it is rarely found in a pure form. I shall call it cosmic religious feeling. It is very difficult to elucidate this feeling to anyone who is entirely without it, especially as there is no anthropomorphic conception of God corresponding to it. The individual feels the futility of human desires and aims, and the sublimity and marvelous order which reveal themselves both in nature and in the world of thought. Individual existence impresses him as a sort of prison, and he wants to experience the universe as a single, significant whole. The beginnings of cosmic religious feeling already appear at an early stage of development, e.g., in many of the Psalms of David, and in some of the prophets. Buddhism, as we have learned especially from the wonderful writings of Schopenhauer, contains a much stronger element of this. The religious geniuses of all ages have been distinguished by this kind of religious feeling, which knows no dogma and no God conceived in man's image, so that there can be no church whose central teachings are based on it. Hence it is precisely among the heretics of every age that we find men who were filled with this highest kind of religious feeling and were in many cases regarded by their contemporaries as atheists, sometimes also as saints. Looked at in this light, men like Democritus, Francis of Assisi, and Spinoza are closely akin to one another. How can cosmic religious feeling be communicated from one person to another if it can give rise to no definite notion of a God and no theology? In my view, it is the most important function of art and science to awaken this feeling and keep it alive in those who are receptive to it. We thus arrive at a conception of the relation of science to religion very different from the usual one. When one views the matter historically, one is inclined to look upon science and religion as irreconcilable antagonists, and for a very obvious reason. The man who is thoroughly convinced of the universal operation of the law of causation cannot for a moment entertain the idea of a being who interferes in the course of events, provided, of course, that he takes the hypothesis of causality really seriously. He has no use for the religion of fear, and equally little for social or moral religion. A God who rewards and punishes is inconceivable to him, for the simple reason that a man's actions are determined by necessity, external and internal, so that in God's eyes he cannot be responsible, any more than an inanimate object is responsible for the motions it undergoes. Science has therefore been charged with undermining morality, but the charge is unjust. A man's ethical behavior should be based effectually on sympathy, education, and social ties and needs. No religious basis is necessary. Man would indeed be in a poor way if he had to be restrained by fear of punishment and hopes of reward after death. It is therefore easy to see why the churches have always fought science and persecuted its devotees. On the other hand, I maintain that the cosmic religious feeling is the strongest and noblest motive for scientific research. Only those who realize the immense efforts, and above all, the devotion without which pioneer work in theoretical science cannot be achieved, are able to grasp the strength of the emotion out of which alone such work, remote as it is from the immediate realities of life, can issue. What a deep conviction of the rationality of the universe, and what a yearning to understand, were it but a feeble reflection of the mind revealed in this world, Kepler and Newton must have had to enable them to spend years of solitary labor in disentangling the principles of celestial mechanics. Those whose acquaintance with scientific research is derived chiefly from its practical results easily develop a completely false notion of the mentality of the men who, surrounded by a skeptical world, have shown the way to kindred spirits scattered wide through the world and through the centuries. Only one who has devoted his life to similar ends can have a vivid realization of what has inspired these men and given them the strength to remain true to their purpose in spite of countless failures. It is cosmic religious feeling that gives a man such strength. A contemporary has said, not unjustly, that in this materialistic age of ours, the serious scientific workers are the only profoundly religious people. Science and religion. Part 2. During the last century and part of the one before, it was widely held that there was an unreconcilable conflict between knowledge and belief. The opinion prevailed among advanced minds that it was time that belief should be replaced increasingly by knowledge. Belief that did not itself rest on knowledge was superstition, and as such had to be opposed. According to this conception, the sole function of education was to open the way to thinking and knowing, and the school, as the outstanding organ for the people's education, must serve that end exclusively. One will probably find, but rarely, if at all, the rationalistic standpoint expressed in such crass form. For any sensible man would see at once how one-sided is such a statement of the position. But it is just as well to state a thesis starkly and nakedly, if one wants to clear up one's mind as to its nature. It is true that convictions can best be supported with experience and clear thinking. On this point, one must agree unreservedly with the extreme rationalist. The weak point of his conception is, however, this, that those convictions which are necessary and determinant for our conduct and judgments cannot be found solely along this solid scientific way. For the scientific method can teach us nothing else beyond how facts are related to and conditioned by each other. The aspiration towards such objective knowledge belongs to the highest of which man is capable, and you will certainly not suspect me of wishing to belittle the achievements and the heroic efforts of man in this sphere. Yet it is equally clear that knowledge of what is does not open the door directly to what should be. One can have the clearest and most complete knowledge of what is, and yet not be able to deduct from that what should be the goal of our human aspirations. Objective knowledge provides us with powerful instruments for the achievements of certain ends, but the ultimate goal itself and the longing to reach it must come from another source. And it is hardly necessary to argue for the view that our existence and our activity acquire meaning only by the setting up of such a goal and of corresponding values. The knowledge of truth as such is wonderful, but it is so little capable of acting as a guide that it cannot prove even the justification and the value of the aspiration toward that very knowledge of truth. Here we face, therefore, the limits of the purely rational conception of our existence. But it must not be assumed that intelligent thinking can play no part in the formation of the goal and of ethical judgments. When someone realizes that for the achievement of an end, certain means would be useful, the means itself becomes thereby an end. Intelligence makes clear to us the interrelation of means and ends, but mere thinking cannot give us a sense of the ultimate and fundamental ends. To make clear these fundamental ends and valuations, and to set them fast in the emotional life of the individual, seems to me precisely the most important function which religion has to perform in the social life of man. And if one asks whence derives the authority of such fundamental ends, since they cannot be stated and justified merely by reason, one can only answer, they exist in a healthy society as powerful traditions which act upon the conduct and aspirations and judgments of the individuals. They are there, that is, as something living, without its being necessary to find justification for their existence. They come into being not through demonstration, but through revelation, through the medium of powerful personalities. One must not attempt to justify them, but rather to sense their nature simply and clearly. The highest principles for our aspirations and judgments are given to us in the Jewish Christian religious tradition. It is a very high goal, which, with our weak powers, we can reach only very inadequately, but which gives a sure foundation to our aspirations and valuations. If one were to take that goal out of its religious form and look merely at its purely human side, one might state it perhaps thus: free and responsible development of the individual, so that he may place his powers freely and gladly in the service of all mankind. There is no room in this for the divinization of a nation, of a class, let alone of an individual. Are we not all children of one Father, as it is said in religious language? Indeed, even the divinization of humanity, as an abstract totality, would not be in the spirit of that ideal. It is only to the individual that a soul is given. And the high destiny of the individual is to serve rather than to rule, or to impose himself in any other way. If one looks at the substance rather than at the form, then one can take these words as expressing also the fundamental democratic position. The true democrat can worship his nation as little as can the man who is religious, in our sense of the term. What then, in all this, is the function of education and of the school? They should help the young person to grow up in such a spirit that these fundamental principles should be to him as the air which he breathes. Teaching alone cannot do that. If one holds these high principles clearly before one's eyes and compares them with the life and spirit of our times, then it appears glaringly that civilized mankind finds itself at present in grave danger. In the totalitarian states, it is the rulers themselves who strive actually to destroy that spirit of humanity. In less threatened parts, it is nationalism and intolerance, as well as the oppression of the individuals by economic means, which threaten to choke these most precious traditions. A realization of how great is the danger is spreading, however, among thinking people, and there is much search for means with which to meet the danger, means in the field of national and international politics, of legislation, or organization in general. Such efforts are, no doubt, greatly needed. Yet the ancients knew something which we seem to have forgotten. All means prove but a blunt instrument, if they have not behind them a living spirit. But if the longing for the achievement of the goal is powerfully alive within us, then shall we not lack the strength to find the means for reaching the goal and for translating it into deeds. It would not be difficult to come to an agreement as to what we understand by science. Science is the century-old endeavor to bring together, by means of systematic thought, the perceptible phenomena of this world into as thoroughgoing an association as possible. To put it boldly, it is the attempt at the posterior reconstruction of existence by the process of conceptualization. But when asking myself what religion is, I cannot think of the answer so easily. And even after finding an answer which may satisfy me at this particular moment, I still remain convinced that I can never, under any circumstances, bring together, even to a slight extent, the thoughts of all those who have given this question serious consideration. At first, then, instead of asking what religion is, I should prefer to ask what characterizes the aspirations of a person who gives me the impression of being religious. A person who is religiously enlightened appears to me to be one who has, to the best of his ability, liberated himself from the fetters of his selfish desires and is preoccupied with thoughts, feelings, and aspirations to which he clings because of their superpersonal value. It seems to me that what is important is the force of this superpersonal content and the depth of the conviction concerning its overpowering meaningfulness, regardless of whether any attempt is made to unite this content with a divine being. For otherwise, it would not be possible to count Buddha and Spinoza as religious personalities. Accordingly, a religious person is devout in the sense that he has no doubt of the significance and loftiness of those superpersonal objects and goals which neither require nor are capable of rational foundation. They exist with the same necessity and matter-of-factness as he himself. In this sense, religion is the age-old endeavor of mankind to become clearly and completely conscious of these values and goals and constantly to strengthen and extend their effect. If one conceives of religion and science according to these definitions, then a conflict between them appears impossible. For science can only ascertain what is, but not what should be, and outside of its domain value judgments of all kinds remain necessary. Religion, on the other hand, deals only with evaluations of human thought and action. It cannot justifiably speak of facts and relationships between facts. According to this interpretation, the well-known conflicts between religion and science in the past must all be ascribed to a misapprehension of the situation which has been described. For example, a conflict arises when a religious community insists on the absolute truthfulness of all statements recorded in the Bible. This means an intervention on the part of religion into the sphere of science. This is where the struggle of the Church against the doctrines of Galileo and Darwin belongs. On the other hand, representatives of science have often made an attempt to arrive at fundamental judgments with respect to values and ends on the basis of scientific method, and in this way have set themselves in opposition to religion. These conflicts have all sprung from fatal errors. Now, even though the realms of religion and science in themselves are clearly marked off from each other, nevertheless, there exist between the two strong, reciprocal relationships and dependencies. Though religion may be that which determines the goal, it has nevertheless learned from science, in the broadest sense, what means will contribute to the attainment of the goals it has set up. But science can only be created by those who are thoroughly imbued with the aspiration toward truth and understanding. This source of feeling, however, springs from the sphere of religion. To this, there also belongs the faith in the possibility that the regulations valid for the world of existence are rational, that is, comprehensible to reason. I cannot conceive of a genuine scientist without that profound faith. The situation may be expressed by an image. Science without religion is lame. Religion without science is blind. Though I have asserted above that in truth a legitimate conflict between religion and science cannot exist, I must nevertheless qualify this assertion once again on an essential point, with reference to the actual content of historical religions. This qualification has to do with the concept of God. During the youthful period of mankind's spiritual evolution, human fantasy created gods in man's own image, who, by the operations of their will, were supposed to determine, or at any rate to influence, the phenomenal world. Man sought to alter the disposition of these gods in his own favor by means of magic and prayer. The idea of God in the religions taught at present is a sublimation of that old concept of the gods. Its anthropomorphic character is shown, for instance, by the fact that men appeal to the divine being in prayers and plead for the fulfillment of their wishes. Nobody, certainly, will deny that the idea of the existence of an omnipotent, just, and omnibeneficent personal God is able to accord man solace, help, and guidance. Also, by virtue of its simplicity, it is accessible to the most undeveloped mind. But on the other hand, there are decisive weaknesses attached to this idea in itself, which have been painfully felt since the beginning of history. That is, if this being is omnipotent, then every occurrence, including every human action, every human thought, and every human feeling and aspiration, is also his work. How is it possible to think of holding men responsible for their deeds and thoughts before such an almighty being? In giving out punishment and rewards, he would to a certain extent be passing judgment on himself. How can this be combined with the goodness and righteousness ascribed to him? The main source of the present-day conflicts between the spheres of religion and of science lies in this concept of a personal God. It is the aim of science to establish general rules which determine the reciprocal connection of objects and events in time and space. For these rules, or laws of nature, absolutely general validity is required, but proven. It is mainly a program, and faith in the possibility of its accomplishment in principle is only founded on partial successes. But hardly anyone could be found who would deny these partial successes and ascribe them to human self-deception. The fact that on the basis of such laws we are able to predict the temporal behavior of phenomena in certain domains with great precision and certainty is deeply embedded in the consciousness of the modern man, even though he may have grasped very little of the contents of those laws. He need only consider that planetary courses within the solar system may be calculated in advance, with great exactitude, on the basis of a limited number of simple laws. In a similar way, though not with the same precision, it is possible to calculate in advance the mode of operation of an electric motor, a transmission system, or of a wireless apparatus, even when dealing with a novel development. To be sure, when the number of factors coming into play in a phenomenological complex is too large, scientific method, in most cases, fails us. One need only think of the weather, in which case prediction even for a few days ahead is impossible. Nevertheless, no one doubts that we are confronted with a causal connection whose causal components are in the main known to us. Occurrences in this domain are beyond the reach of exact prediction because of the variety of factors in operation, not because of any lack of order in nature. We have penetrated far less deeply into the regularities obtaining within the realm of living things, but deeply enough, nevertheless, to sense at least the rule of fixed necessity. One need only think of the systematic order in heredity, and in the effect of poisons, as for instance alcohol, on the behavior of organic beings. What is still lacking here is a grasp of connections of profound generality, but not a knowledge of order in itself. The more a man is imbued with the ordered regularity of all events, the firmer becomes his conviction that there is no room left by the side of this ordered regularity for causes of a different nature. For him neither the rule of human nor the rule of divine will exists as an independent cause of natural events. To be sure, the doctrine of a personal God interfering with natural events could never be refuted, in the real sense, by science, for this doctrine can always take refuge in those domains in which scientific knowledge has not yet been able to set foot. But I am persuaded that such behavior on the part of the representatives of religion would not only be unworthy, but also fatal. For a doctrine which is able to maintain itself not in clear light, but only in the dark, will of necessity lose its effect on mankind, with incalculable harm to human progress. In their struggle for the ethical good, teachers of religion must have the stature to give up the doctrine of a personal God, that is, give up that source of fear and hope, which in the past placed such vast power in the hands of priests. In their labors, they will have to avail themselves of those forces which are capable of cultivating the good, the true, and the beautiful in humanity itself. This is, to be sure, a more difficult but an incomparably more worthy task. This thought is convincingly presented in Herbert Samuel's book, Belief and Action. After religious teachers accomplish the refining process, indicated they will surely recognize with joy that true religion has been ennobled and made more profound by scientific knowledge. If it is one of the goals of religion to liberate mankind as far as possible from the bondage of egocentric cravings, desires, and fears, scientific reasoning can aid religion in yet another sense. Although it is true that it is the goal of science to discover rules which permit the association and foretelling of facts, this is not its only aim. It also seeks to reduce the connections discovered to the smallest possible number of mutually independent conceptual elements. It is in this striving after the rational unification of the manifold that it encounters its greatest successes, even though it is precisely this attempt which causes it to run the greatest risk of falling a prey to illusions. But whoever has undergone the intense experience of successful advances made in this domain is moved by profound reverence for the rationality made manifest in existence. By way of the understanding, he achieves a far-reaching emancipation from the shackles of personal hopes and desires, and thereby attains that humble attitude of mind toward the grandeur of reason, incarnate in existence, and which, in its profoundest depths, is inaccessible to man. This attitude, however, appears to me to be religious, in the highest sense of the word, and so it seems to me that science not only purifies the religious impulse of the dross of its anthropomorphism, but also contributes to a religious spiritualization of our understanding of life. The further the spiritual evolution of mankind advances, the more certain it seems to me that the path to genuine religiosity does not lie through the fear of life, and the fear of death, and blind faith, but through striving after rational knowledge. In this sense, I believe that the priest must become a teacher if he wishes to do justice to his lofty educational mission. Religion and science. Irreconcilable. Part 3. Does there truly exist an insuperable contradiction between religion and science? Can religion be superseded by science? The answers to these questions have, for centuries, given rise to considerable dispute and, indeed, bitter fighting. Yet, in my own mind, there can be no doubt that in both cases, a dispassionate consideration can only lead to a negative answer. What complicates the solution, however, is the fact that while most people readily agree on what is meant by science, they are likely to differ on the meaning of religion. As to science, we may well define it for our purpose as methodical thinking, directed toward finding regulative connections between our sensual experiences. Science, in the immediate, produces knowledge and indirectly means of action. It leads to methodical action if definite goals are set up in advance. For the function of setting up goals and passing statements of value transcends its domain. While it is true that science, to the extent of its grasp of causative connections, may reach important conclusions as to the compatibility and incompatibility of goals and evaluations, the independent and fundamental definitions regarding goals and values remain beyond science's reach. As regards religion, on the other hand, one is generally agreed that it deals with goals and evaluations, and, in general, with the emotional foundation of human thinking and acting, as far as these are not predetermined by the inalterable hereditary disposition of the human species. Religion is concerned with man's attitude toward nature at large, with the establishing of ideals for the individual and communal life, and with mutual human relationship. These ideals religion attempts to attain by exerting an educational influence on tradition, and through the development and promulgation of certain easily accessible thoughts and narratives, epics and myths, which are apt to influence evaluation and action along the lines of the accepted ideals. It is this mythical, or rather this symbolic, content of the religious traditions which is likely to come into conflict with science. This occurs whenever this religious stock of ideas contains dogmatically fixed statements on subjects which belong in the domain of science. Thus, it is of vital importance for the preservation of true religion that such conflicts be avoided when they arise from subjects which, in fact, are not really essential for the pursuance of the religious aims. When we consider the various existing religions as to their essential substance, that is, divested of their myths, they do not seem to me to differ as basically from each other as the proponents of the relativistic or conventional theory wish us to believe. And this is by no means surprising. For the moral attitudes of a people that is supported by religion need always aim at preserving and promoting the sanity and vitality of the community and its individuals, since otherwise this community is bound to perish. A people that were to honor falsehood, defamation, fraud, and murder would be unable, indeed, to subsist for very long. When confronted with a specific case, however, it is no easy task to determine clearly what is desirable and what should be eschewed, just as we find it difficult to decide what exactly it is that makes good painting or good music. It is something that may be felt intuitively more easily than rationally comprehended. Likewise, the great moral teachers of humanity were, in a way, artistic geniuses in the art of living. In addition to the most elementary precepts directly motivated by the preservation of life and the sparing of unnecessary suffering, there are others to which, although they are apparently not quite commensurable to the basic precepts, we nevertheless attach considerable importance. Should truth, for instance, be sought unconditionally, even where its attainment and its accessibility to all would entail heavy sacrifices in toil and happiness? There are many such questions which, from a rational vantage point, cannot easily be answered or cannot be answered at all. Yet, I do not think that the so-called relativistic viewpoint is correct, not even when dealing with the more subtle moral decisions. When considering the actual living conditions of present-day civilized humanity from the standpoint of even the most elementary religious commands, one is bound to experience a feeling of deep and painful disappointment at what one sees. For while religion prescribes brotherly love in the relations among the individuals and groups, the actual spectacle more resembles a battlefield than an orchestra. Everywhere, in economic as well as in political life, the guiding principle is one of ruthless striving for success at the expense of one's fellow men. This competitive spirit prevails even in school, and destroying all feelings of human fraternity and cooperation, conceives of achievement not as derived from the love for productive and thoughtful work, but as springing from personal ambition and fear of rejection. There are pessimists who hold that such a state of affairs is necessarily inherent in human nature. It is those who propound such views that are the enemies of true religion, for they imply thereby that religious teachings are utopian ideals and unsuited to afford guidance in human affairs. The study of the social patterns in certain so-called primitive cultures, however, seems to have made it sufficiently evident that such a defeatist view is wholly unwarranted. Whoever is concerned with this problem, a crucial one in the study of religion as such, is advised to read the description of the Pueblo Indians in Ruth Benedict's book, Patterns of Culture. Under the hardest living conditions, this tribe has apparently accomplished the difficult task of delivering its people from the scourge of competitive spirit and of fostering in it a temperate cooperative conduct of life, free of external pressure and without any curtailment of happiness. The interpretation of religion, as here advanced, implies a dependence of science on the religious attitude, a relation which, in our predominantly materialistic age, is only too easily overlooked. While it is true that scientific results are entirely independent from religious or moral considerations, those individuals to whom we owe the great creative achievements of science were all of them imbued with the truly religious conviction that this universe of ours is something perfect and susceptible to the rational striving for knowledge. If this conviction had not been a strongly emotional one, and if those searching for knowledge had not been inspired by Spinoza's Amor Dei Intellectualis, they would hardly have been capable of that untiring devotion which alone enables man to attain his greatest achievements. The Theory of Relativity and Its Influence on Scientific Thought, by Arthur Stanley Eddington. In the days before Copernicus, the Earth was, so it seemed, an immovable foundation on which the whole structure of the heavens was reared. Man, favorably situated at the hub of the universe, might well expect that to him the scheme of nature would unfold itself in its simplest aspect. But the behavior of the heavenly bodies was not at all simple, and the planets literally looped the loop in fantastic curves called epicycles. The cosmogonist had to fill the skies with spheres revolving upon spheres to bear the planets in their appointed orbits. And wheels were added to wheels until the music of the spheres seemed well nigh drowned in a discord of whirling machinery. Then came one of the great revolutions of scientific thought, which swept aside the Ptolemaic system of spheres and epicycles, and revealed the simple plan of the solar system, which has endured to this day. The revolution consisted in changing the viewpoint from which the phenomena were regarded. As presented to the Earth, the track of a planet is an elaborate epicycle, but Copernicus bade us transfer ourselves to the Sun and look again. Instead of a path with loops and nodes, the orbit is now seen to be one of the most elementary curves, an ellipse. We have to realize that the little planet on which we stand is of no great account in the general scheme of nature. To unravel that scheme, we must first disembarrass nature of the distortions arising from the local point of view from which we observe it. The Sun, not the Earth, is the real center of the scheme of things, at least of those things in which astronomers at that time had interested themselves, and by transferring our viewpoint to the Sun, the simplicity of the planetary system becomes apparent. The need for a cumbrous machinery of spheres and wheels has disappeared. Everyone now admits that the Ptolemaic system, which regarded the Earth as the center of all things, belongs to the Dark Ages. But to our dismay, we have discovered that the same geocentric outlook still permeates modern physics through and through, unsuspected until recently. It has been left to Einstein to carry forward the revolution begun by Copernicus, to free our conception of nature from the terrestrial bias imported into it by the limitations of our earthbound experience. To achieve a more neutral point of view, we have to imagine a visit to some other heavenly body. That is a theme which has attracted the popular novelist, and we often smile at his mistakes when, sooner or later, he forgets where he is supposed to be and endows his voyagers with some purely terrestrial appanage impossible on the star they are visiting. But scientific men, who have not the novelist's license, have made the same blunder. When, following Copernicus, they station themselves on the Sun, they do not realize that they must leave behind a certain purely terrestrial appanage, namely, the frame of space and time in which men on this earth are accustomed to locate the events that happen. It is true that the observer on the Sun will still locate his experiences in a frame of space and time if he uses the same faculties of perception and the same methods of scientific measurement as on the Earth. But the solar frame of space and time is not precisely the same as the terrestrial frame, as we shall presently see. I think you will readily understand what is meant by a frame of space and time. It is the system of location to which we appeal when we state, for example, that one event is 100 miles distant from and 10 hours later than another. The terms space and time have not only a vague descriptive reference to a boundless void and an ever-rolling stream, but denote an exact quantitative system of reckoning distances and time intervals. Einstein's first great discovery was that there are many such systems of reckoning, many possible frames of space and time, exactly on all fours with one another. No one of these can be distinguished as more fundamental than the rest. No one frame rather than another can be identified as the scaffolding used in the construction of the world. And yet one of them does present itself to us as being the actual space and time of our experience, and we recoil from the other equivalent frames which seem to us artificial systems in which distance and duration are mixed up in an extraordinary way. What is the cause of this invidious selection? It is not determined by anything distinctive in the frame. It is determined by something distinctive in us, by the fact that our existence is bound to a particular planet, and our motion is the motion of that planet. Nature offers an infinite choice of frames. We select the one in which we and our petty terrestrial concerns take the most distinguished position. Our mischievous geocentric outlook has cropped out again unsuspected, persuading us to insist on this terrestrial space-time frame, which in the general scheme of nature is in no way superior to other frames. The more closely we examine the processes by which events are assigned to their positions in space and time, the more clearly do we see that our local circumstances play a considerable part in it. We have no more right to expect that the space-time frame on the Sun will be identical with our frame on the Earth than to expect that the force of gravity will be the same there as here. If there were no experimental evidence in support of Einstein's theory, it would nevertheless have made a notable advance by exposing a fallacy underlying the older mode of thought, the fallacy of attributing, unquestioningly, a more than local significance to our terrestrial reckoning of space and time. But there is abundant experimental evidence for detecting and determining the difference between the frames of differently circumstanced observers. Much of the evidence is too technical to be discussed here, and I can only refer to the Michelson-Morley experiment. I fear that some of you must be getting rather tired of the Michelson-Morley experiment, but those who go to a performance of Hamlet have to put up with the Prince of Denmark. This famous experiment is a simple test whether light travels at the same speed in two different directions. For this purpose, an apparatus is constructed with two equal arms at right angles, providing two equal tracks for the light. A beam of light is divided into two parts, so that one part travels along one arm and back, and the other along the other arm and back. The two rays then reunite, and by delicate interference tests it is possible to tell if one has been delayed more than the other. A delay of less than 1,000 billionth of a second could be detected. The experiment is simply a race between two light rays with equal tracks, but pointing in different directions. The result turns out to be a dead heat. At first sight, this is just what would be expected, and one almost wonders why it should have been thought worthwhile to try the experiment. But Michelson, like a good Copernican, had stationed himself on the sun to watch the race. Accordingly, he realized that the apparatus was being borne along by the Earth's orbital motion with a speed of 20 miles a second. Consequently, the light does not travel exactly the double length of the arm. Starting at one end, it has to go to the turning mark at the other end, which has moved on a little in the meantime. Then it returns to the place which the starting mark has travelled to whilst the race is in progress. That does not add up to exactly the double length of the arm. Making the calculations, we easily find that although the two arms are equal, the two light journeys are unequal. The competitor whose track lies in the line of the Earth's motion has the longer journey and is at a disadvantage, and yet according to the experiment, he does not suffer the expected delay. From our standpoint on the Sun, the experiment seems to have gone wrong. Copernicus has met with a rebuff, and Ptolemy is triumphant. But that is because we have not admitted the full consequences of transferring our standpoint to the Sun. We have all the while been keeping one foot on Earth. Of course, the whole experiment turns on the two arms having been first adjusted to perfect equality. This could only be ascertained by experiment, and the test applied was to rotate the apparatus through a right angle, so that if, for example, the journey in the line of the Earth's motion had had the advantage of the shorter arm on one occasion, the transverse journey would have had it on the repetition. That is a perfectly satisfactory test for a terrestrial observer. To turn a rod from one direction to another is the simple and direct way of marking out equal lengths. But the test is not satisfactory to an observer on the Sun. He would not think of attempting to partition equal lengths of space by means of rods travelling at 20 miles a second. His frame of space, the space not only of refined measurement, but also of the cruder measurements made with the sense organs of his body which determine his perception of space, is partitioned by appliances at rest relatively to him, e.g., his own eyes and limbs. Lengths of objects carried on the Earth must be judged by him according to the room they occupy in his own frame. In the space of the terrestrial observer, the two arms of the apparatus were adjusted to equal length. But in the repartitioned space of the solar observer, they may quite well occupy unequal lengths, and when we take the viewpoint of an observer on the Sun, we must not overlook this inequality. This inequality is not so much an hypothesis proposed to account for Michelson's result as a direct deduction from it. The two light journeys were found to occupy equal times. This clearly shows that the arm in the less favoured direction is shorter than the other, so as to counterbalance the handicap to which I have referred. When the apparatus is turned through a right angle, the experiment still gives the same result. It does not matter which of the two arms we place in the line of the Earth's motion. That arm must be shorter than the other. In other words, each arm must automatically contract when it is turned from the transverse to the longitudinal position with respect to its line of motion. This is the famous Fitzgerald contraction of a moving rod. It is of the same amount whatever the material of the rod, and depends only on the speed of its motion. For the Earth's orbital motion, the contraction amounts to 1 part in 200 million. In fact, the Earth's diameter in the direction of its motion is always shortened by 212 inches, the transverse diameter being unaffected. This contraction of a moving material object was first revealed to us by the Michelson-Morley experiment. But it is not at all disagreeable to theoretical anticipations. We have to remember that a rod consists of a large number of molecules kept in position by their mutual forces. The chief force is the force of cohesion, and there is little doubt that this is of electrical nature. But when the rod is set in motion, the electrical forces inside it must change. For example, each electric charge, when put in motion, becomes an electric current, and the currents will exert magnetic attractions on each other, which did not occur in the system at rest. Under the new system of forces, the molecules will have to find new positions of equilibrium. They become differently spaced. And it is therefore not surprising that the form of the rod changes. Without going beyond the classical laws of Maxwell, we can anticipate theoretically what will be the new equilibrium state of the rod, and it turns out to be contracted to the exact amount required by the Michelson-Morley result. The contraction of the moving rod ought not to surprise us. It would be much more surprising if the rod were to maintain the same form in spite of the alteration of the electrical forces which determine the spacing of the molecules. But the remarkable thing is that the contraction is only apparent according to the outlook of the solar observer. And we, on the Earth, who travel with the rod, cannot appreciate it. The fact that the contraction happens to be very small is irrelevant. For convenience, suppose that the Earth's velocity is 8,000 times faster, so that the contraction amounts to something like a half the original length. We should still fail to notice it in everyday life. Let us say that the direction of the Earth's motion is vertically upwards. I turn my arm from horizontal to vertical, and it contracts to half its length. No, you cannot convince me I am wrong. I am not afraid of a yard measure. Bring one and measure my arm. First horizontally, the result is 30 inches. Now vertically, the result is 30 half inches. Because you must remember that you have turned the scale into the line of the Earth's motion, so that each inch division contracts to half an inch. But we can see that your arm does not contract. Are we not to trust our eyes? Certainly not, unless you first correct your visual impressions for the contraction of the retina in the vertical direction, and for the effect of our rapid motion on the apparent direction of propagation of the waves of light. You will find, when you calculate these corrections, that they just conceal the contraction. But if the contraction takes place, ought one not to feel it happening to the arm? Not necessarily. I am an observer on the Earth, and my feelings, like other sense impressions, belong to the geocentric outlook on nature, which Copernicus has persuaded us to abandon. Take a pair of compasses and twiddle them on a sheet of paper. Is the resulting curve a circle or an ellipse? Copernicus, from his standpoint on the Sun, declares that owing to the Fitzgerald contraction, the 2 points drew nearer together when turned in the direction of the Earth's orbital motion. Hence the curve is flattened into an ellipse. But here I think Ptolemy has a right to be heard. He points out that from the beginning of geometry, circles have always been drawn with compasses in this way, and that when the word circle is mentioned, every intelligent person understands that this is the curve meant. The same pencil line is in fact a circle in the space of the terrestrial observer and an ellipse in the space of a solar observer. It is at the same time a moving ellipse and a stationary circle. I think that illustrates as well as possible what we mean by the relativity of space. It is sometimes complained that Einstein's conclusion that the frame of space and time is different for observers with different motions tends to make a mystery of a phenomenon which is not, after all, intrinsically strange. We have seen that it depends on a contraction of moving objects, which turns out to be quite in accordance with Maxwell's classical theory. But even if we have succeeded in explaining it to ourselves intelligibly, that does not make the statement any the less true. A new result may often be expressed in various ways. One mode of statement may sound less mysterious, but another mode may show more clearly what will be the consequences in amending and extending our knowledge. It is for the latter reason that we emphasize the relativity of space, that lengths and distances differ according to the observer implied. Distance and duration are the most fundamental terms in physics. Velocity, acceleration, force, energy, and so on, all depend on them. And we can scarcely make any statement in physics without direct or indirect reference to them. Surely then we can best indicate the revolutionary consequences of what we have learnt by the statement that distance and duration and all the physical quantities derived from them do not, as hitherto supposed, refer to anything absolute in the external world, but are relative quantities which alter when we pass from one observer to another with different motion. The consequence in physics of the discovery that a yard is not an absolute chunk of space, and that what is a yard for one observer may be 18 inches for another observer, may be compared with the consequences in economics of the discovery that a pound sterling is not an absolute quantity of wealth, and in certain circumstances may really be 7 and 6pence. The theorist may complain that this last statement tends to make a mystery of phenomena of currency, which have really an intelligible explanation. But it is a statement which commends itself to the man who has an eye to the practical applications of currency. Ptolemy on the earth and Copernicus on the sun are both contemplating the same external universe. But their experiences are different, and it is in the process of experiencing events that they become fitted into the frame of space and time, the frame being different according to the local circumstances of the observer who is experiencing them. That, I take it, is Kant's doctrine. Space and time are forms of experience. The frame then is not in the world. It is supplied by the observer and depends on him. And those relations of simplicity which we seek when we try to obtain a comprehension of how the universe functions must lie in the events themselves before they have been arbitrarily fitted into the frame. The most we can hope for from any frame is that it will not have distorted the simplicity which was originally present, whilst an ill-chosen frame may play havoc with the natural simplicity of things. We have seen that the simplicity of planetary motions was obscured in Ptolemy's frame and became apparent in Copernicus's frame. But for ordinary terrestrial phenomena, the position is reversed, and Ptolemy's frame allows their natural simplicity to become apparent. In Copernicus's frame, the most simple phenomena are brought about by highly complicated processes which mutually cancel one another. Ordinary objects contract and expand as they are moved about, and the changes are concealed by an elaborate conspiracy in which all the quantities of nature, electrical, optical, mechanical, gravitational, have joined. In Copernicus's frame, we have a great complication of description which has no counterpart in anything occurring in the external world, because the terms of our description refer to the irrelevant process of fitting into the selected frame of space and time. This elaborate Copernican scheme rather reminds one of the schemes of the White Knight. But I was thinking of a plan, to dye one's whiskers green, and always use so large a fan that they could not be seen. We do not deny the subtlety and the remarkable efficiency of the plan, but we may be allowed to question whether it is the simplest interpretation of the drab monotony of the face of nature presented to us. The simple fact is that a terrestrial or Ptolemaic frame fits naturally the terrestrial phenomena, and a solar or Copernican frame fits the phenomena of the solar system. But we cannot make one frame serve for both without introducing irrelevant complications. We go beyond Copernicus nowadays and are not content with a visit to the sun. Why choose the sun rather than some other star in order to obtain an undistorted view of things? The astronomer now places himself so as to travel with the center of gravity of the stellar universe and is not even then quite satisfied. The physicist dreams of a land of Weisnichtwo, which shall be truly at rest in the ether. We realize the distortion imported into the world of nature by the parochial standpoint from which we observe it, and we try to place ourselves so as to eliminate this distortion, so as to observe that which actually is. But it is a vain pursuit. Wherever we pitch our camera, the photograph is necessarily a two-dimensional picture, distorted according to the laws of perspective. It is never a true semblance of the building itself. We must try another plan. I do not think we can ever eliminate altogether the human element in our conception of nature. But we can eliminate a particular human element, namely, this framework of space and time. If our thought must be anthropocentric, it need not be geocentric. Nor are we permanently better off if we merely substitute the space-time frame of some other star or standard of motion. We must leave the frame entirely indeterminate. When we do that, we find that the world common to all observers, in which each observer traces a different space-time frame according to his own outlook, is a world of 4 dimensions. When we look at any object, say a chair, the impression on our eyes is a 2-dimensional picture depending on the position from which we are looking. But we have no difficulty in conceiving of the chair as a solid object, not to be identified with any one of our 2-dimensional pictures of it, but giving rise them all as the position of the observer is varied. We must now realize that this solid chair in 3 dimensions is itself only an appearance, which changes according to the motion of the observer, and that there is a super-object in 4 dimensions, not to be identified with the 3-dimensional chair in Ptolemy's scheme, or the same chair in Copernicus's scheme, but giving rise to both these appearances. The synthesis of a 3-dimensional chair from a number of flat pictures is easy to us because we are accustomed to assume different positions in rapid succession. Indeed, our 2 eyes give us slightly different points of view simultaneously. By sheer necessity, our brains have been forced to construct the conception of the solid chair to combine these changing appearances. But we do not vary our motion to any appreciable extent, and our brains have not hitherto been called upon to combine the appearances for different motions. Thus, the effort which we now ask the brain to make is a novel one. That explains why the result seems to transcend our ordinary mode of thought. The discovery, or one should rather say, the rediscovery of the world of 4 dimensions, is due to Minkowski. Einstein had worked out fully the relations between the frames of space and time for observers with different motions. To the genius of Minkowski, we owe the realization that these frames are merely systems of partitions, arbitrarily drawn across a 4-dimensional world which is common to all observers. There is a strange delusion that the 4th dimension must be something wholly beyond the conception of the ordinary man, and that only the mathematician can be initiated into its mysteries. It is true that the mathematician has the advantage of understanding the technical machinery for solving the problems which may arise in studying the world of 4 dimensions. But as regards the conception of the 4 dimensions of the world, his point of view is the same as that of anybody else. Is it supposed that by intense thought he throws himself into some state of trance in which he perceives some hitherto unsuspected direction stretching away at right angles to length, breadth, and thickness? That would not be much use. The world of 4 dimensions, of which we are now speaking, is perfectly familiar to everybody. It is obvious to everyone, even to the mathematician, that the world of solid and permanent objects has 3 dimensions and no more. That objects are arranged in a 3-fold order, which for any particular individual may be analyzed into right and left, backwards and forwards, up and down. But it is no less obvious to everyone that the world of events is of 4 dimensions. that events are arranged in a fourfold order, which in the experience of any particular individual will be analyzed into right and left, backwards and forwards, up and down, sooner and later. The subject of our study is external nature, which is a world of events, common to all observers but represented by them differently in their parochial frames of space and time. It is obvious to the most commonplace experience that this absolute world contains a fourfold order. The news that the events around us form a world of 4 dimensions is as stale as the news that Queen Anne is dead. The reason why the relativist resurrects this ancient truism is because it is only in this undissected combination of 4 dimensions that the experiences of all observers meet. In our own experience, one dimension is sharply separated from the other 3 and is distinguished as time. But our experience is solely terrestrial. And if we insist on building the scheme of nature on purely terrestrial experience, we are limiting ourselves to the medieval geocentric system of the world. We have been accustomed to regard the enduring world as composed of a continuous succession of instantaneous states, as though the world of events were stratified. Each event is supposed to lie in a definite instant or stratum, and the orderly succession of these strata makes up the whole of reality. The instant now represents one such stratum running throughout the universe. Indeed, we are accustomed to extend it beyond the universe, and we even use the word now with reference to the existence of those who have passed away from the material world. The investigations of the relativity theory show incontrovertibly that this supposed stratification is an illusion. There is not the slightest evidence for such a view of world structure. The instantaneous state, which we have hitherto taken to be a natural stratum in the 4-dimensional world of events, is merely an arbitrary partition created by ourselves to correspond with our geocentric outlook. We can take a differently inclined partition, that is to say, a section which includes on the one side of us events which happened a little while ago, and on the other side of us events which have not yet happened. Such a farcical combination is in every way equivalent to our so-called instantaneous state, and indeed it is an instantaneous state, according to the outlook of some non-terrestrial observer with suitably assigned motion. It is so contrary to our natural prejudices to recognize that the worldwide instant now is created by ourselves and has no existence apart from our geocentric outlook, that I will spend a few moments trying to show its artificiality. When I say that, I am conscious of an instant now. I am only conscious of it insofar as it is here, inside me. What then has led me to imagine that there exists a continuation of it outside me? It is because I look out on the world and see various events happening now, so that I jump to the conclusion that this instant of which I am conscious has to be extended to include them. But that idea is another inheritance from the Dark Ages, overthrown by Roma in 1675. It is not the events themselves, but the sense impressions to which they give rise, which are happening in the instant now. So my justification for placing the events outside me, in the instance of which I am conscious, has entirely disappeared. Unfortunately, however, the crude outlook was not abolished, but patched up. It was found that the immediate difficulties could be met by locating the external events, not in the instant of our visual perception of them, but in an instant which we had experienced a little time back, allowing, as we say, for the time of propagation of light. Thus our instants were still made to extend through space. But they were carried like partitions among the events by an artificial process of computation, and no longer by immediate intuition. The relativity theory recognizes these worldwide instants for what they are: artificial partitions constructed for purposes of calculation. I may add that it in no way tampers with the local instants which form the stream of our consciousness. It fully recognizes that the chain of events in such a time succession is a series of an entirely distinctive character from the succession of points along a line in space. Those who suspect that Einstein's theory is playing unjustifiable tricks with time should realize that it leaves entirely untouched that time, succession of which we have intuitive knowledge, and confines itself to overhauling the artificial scheme of time which Römer first introduced into physics. The study of the four-dimensional world of events gives us a new insight into the processes of nature, because it removes the irrelevant stratification in a particular direction, the instantaneous states, which we have so unnecessarily introduced in our customary outlook. When this stratification is ignored, we are enabled to see the processes in their simplest aspect, though not, of course, in their most familiar aspect. We must distinguish between simplicity and familiarity. A pig may be most familiar to us in the form of rashes, but the unstratified pig is a simpler object of study to the biologist who wishes to understand how the animal functions. I will conclude this part of the argument with an experimental application which illustrates the power of Einstein's method. Much study has of late been given to electrons moving with very high speeds. For example, the V particles shot off from radioactive substances are negative electrons, which sometimes attain speeds of 100,000 miles a second. It is found by experiment that the rapid motion produces an increase of mass of these particles. I want to show that the theory of relativity gives a very simple explanation of just how this increase of mass occurs. But I must first remark that an explanation had been previously given, which had generally been accepted as satisfactory. The phenomenon was actually predicted by J.J. Thomson before relativity was thought of, because, assuming that the mass of a particle is of electrical origin, an application of Maxwell's equations shows that it ought to increase with velocity. But the precise law of increase cannot be predicted on this basis, since various plausible assumptions lead to slightly different results. Moreover, Maxwell's equations are, after all, only empirical laws, with a mystery of their own. It was a notable advance to connect the change of mass at high speeds with other phenomena whose strangeness has disappeared by a long familiarity. But there is still scope for a more far-reaching explanation. Einstein takes us straight to the root of the mystery, and he clears up one point which was misleading, if not actually wrong, in the older explanation. The change of mass does not in any way depend on whether the mass is of electrical origin or not. It arises simply from the fact that mass is a relative quantity, depending by its definition on the relative quantity's length and time. Let us look at the V particle from its own point of view. It is just an ordinary electron, in no way different from any other. But it is traveling unusually rapidly. That, says the electron, is a matter of opinion. So far as I am aware, I am at rest, if the word rest has any meaning. In fact, I was just contemplating with amazement your extraordinary speed of 100,000 miles a second with which you are shooting past me. Of course, our motion is of no particular concern to the electron, and it will not modify its constitution on our account. So it keeps its mass, radius, electric field, etc., equal to the standard constants applying to electrons in general. These terms are relative, and refer therefore to some particular frame of space and time, clearly the frame appropriate to an electron in self-contemplation, viz., the one with respect to which it is at rest. But this frame is not the usual geocentric frame to which we refer quantities such as length, time, and mass. There is a difference of 100,000 miles a second between our station of observation and that of the V particle in self-contemplation. It is a mere matter of geometry to discover what the V particle's lengths and times become when referred to the partitions which we have drawn across the world. But when we calculate the consequential change of mass resulting from the changes of length and time, we find that it should be increased in precisely the proportion indicated by the most refined experiments. The point is that every electron, at rest or in motion, is a perfectly constant structure, but we distort it by fitting it into the space-time frame appropriate to our own motion, with which the electron has no concern. The greater our motion with respect to the electron, the greater will be the distortion. The distortion is not produced by any physical agency at work in the electron. It is a purely subjective distortion depending on our transformation of the reference frame of space and time. This distortion involves a change in our physical description of the electron in terms of mass, shape, size, and in particular, the change of mass agrees precisely with that found experimentally. You see that it is not altogether idle discussing the natural space-time frames for observers moving with huge velocities. We know of no animate observers with these speeds, but we do know of inanimate material objects. Their common resemblance is obscured when we refer them indiscriminately to our irrelevant geocentric frame. We think they have altered their properties, varied in mass, and so on. But the resemblance is restored when we refer each individual to the frame appropriate to it, and so describe them all in comparable terms. Our measurements of distance in space are found to be subject to certain laws, the laws of geometry, but it has now become impossible to regard the subject of space geometry as complete in itself. Consider a triangle formed by 3 points, or events, in the four-dimensional world. If we happen to have drawn our instantaneous strata so that the 3 points lie in one stratum, then the triangle is a space triangle, and its properties fall within the scope of our classical geometry. But another observer will draw his strata in a different direction, and for him, the triangle would be partly in space and partly in time, so that it would not be a fit subject for space geometry. The subject of geometry is in a desperate condition, because Copernicus and Ptolemy not merely disagree as to the geometry of a configuration, they even disagree as to whether a given configuration is one to which space geometry is applicable. It is clear that to save it, we must extend our geometry so as to include time as well as space. Let me give an illustration of this extension. The terrestrial observer can have a space triangle formed by 3 points or events at the same instant, whose sides he can measure with scales. He can also have a time triangle formed by 3 events on different dates, whose sides he must measure with clocks. You all know the law of the space triangle, that if you measure with a scale from A to B and from B to C, the sum of the readings is always greater than the measure from A to C. It is not so well known that there is a precisely analogous law for the time triangle, that if you measure with a clock from A to B and from B to C, the sum of the readings is always less than the reading of a clock measuring directly from A to C. In the space triangle, any 2 sides are together greater than the third side. In the time triangle, 2 sides are together less than the third side. Both these laws must be combined in our general geometry of 4 dimensions so that it will not be quite so simple a geometry as that to which we are accustomed. But the point to which I would especially direct attention is this. Evidently, the proposition which I have given you about time triangles cannot be dissociated from the corresponding proposition about space triangles. When we give up the medieval geocentric standpoint, we must recognize that they belong to one geometry, of which our ordinary space geometry is only a part or projection. But if you examine the proposition about time triangles, you will see that it is a statement about the behavior of clocks when they move about, a subject which obviously comes under the heading of mechanics. When we deal with the 4-dimensional world, we can no longer distinguish between geometry and mechanics. They become the same subject. When we have completely mastered the geometry of the world of events, we shall have inevitably learnt the mechanics of it. That is why Einstein, studying the geometry of the world and discovering that it was strictly non-Euclidean, found that he was at the same time studying the mechanical force of gravitation. And when he had made up his mind which of the possible varieties of non-Euclidean geometry was obeyed, and so settled the laws of the new geometry, the same decision settled the law of gravitation, a law approximating to, but not identical with, the law which Newton had given. Here a wide vista opens before us. We see that 2 great divisions of mathematical physics, viz., geometry and mechanics, have met in the four-dimensional world. It is not merely that mechanical problems can be treated by formulae originally belonging to pure geometry. That device has long been in use. Experimental geometry and mechanics actually relate to the same subject matter, and the young student who discovers experimental laws with ruler and compasses and cardboard figures, and later goes on to pendulums and spring balances, is developing a single subject which cannot be divided any more than the subject of magnetism can be divided from electricity. It is through this unification of geometry and mechanics that I should like to approach the problem of gravitation, showing that a field of force is a manifestation of the geometry of space and time. But I fear that that would be too technical, so we will approach it from a different angle. We have shown that the contemplation of the world from the standpoint of a single observer is liable to distort its simplicity, and we have tried to obtain a juster idea by taking into account and combining other points of view. The more standpoints, the better. Let us now consider another point of view, which we have not previously thought about, the point of view of an observer who has tumbled out of an aeroplane and is falling headlong. In many respects, his is an ideal situation, temporarily. Unfortunately, on terra firma, we are continually subjected to a very disturbing influence. We undergo a terrific bombardment by the molecules of the ground, which are hammering on the soles of our boots with a total force of some 10 stone weight, pressing us upwards. Now, our bodies are the scientific appliances, which we use to make our common observations of the world. I am sure that no physicist would permit anyone to enter his laboratory and hammer on his clocks and galvanometers whilst he was observing with them. At any rate, he would think it necessary to apply some corrections for the effect of the disturbance. Let us then allow ourselves to fall freely in vacuo. Then we shall be free from this disturbing bombardment, and able to take a much more natural view of what is going on around us. Whilst falling, we perform the experiment of letting go an apple held in the hand. The apple is now free, but it cannot fall any more than it was falling already. Consequently, it remains poised in contact with our hand. In our new outlook, in our new frame of space and time, an apple does not drop. There is no mysterious force accelerating it. And remember that this new frame of space and time is the natural frame of a free observer, whereas the old frame, in which the mysterious accelerating force occurred, was the frame of a very much disturbed observer. It is true that when we look down at the earth, we see trees and houses rushing up to meet us. But there is no mystery about that. There is an obvious cause for it. Plainly they are being propelled upwards from below by that molecular bombardment which I have mentioned. You see that the apple's view of things is simpler than Newton's. Newton had to invent a mysterious force dragging the apple down. The apple observes only a familiar physical agency propelling Newton up. It is not my purpose to emphasize unduly the superiority of the apple's view over Newton's, but rather to regard both on an equal footing. I have perhaps been a little unfair to Newton. His position on the surface of the earth was unfortunate, but he would have been perfectly content to be at the center of the earth, where he could have remained without support, i.e. without disturbance by molecular bombardment. From there, he would still have observed the well-known acceleration of the apple, and the apple would have observed a corresponding acceleration of Newton without any molecular bombardment causing it. From either point of view, there is a mysterious agent at work. How shall we picture to ourselves this agent? Shall we picture it as a force, a tug of some kind? But if so, to which of them is the tug applied? If we take the standpoint of Newton, the tug is applied to the apple. If the standpoint of the apple, the tug is applied to Newton. So that in our synthesis of all standpoints, we cannot decide which is being tugged, and the picture of gravitation as a tugging agent becomes impossible. Einstein replaces it by a different picture, which we shall perhaps better understand if we compare it with a very similar revolution of scientific thought which occurred long ago. The ancients believed that the earth was flat. The small portion of its surface with which they were chiefly concerned, could be represented without serious distortion on a flat map. As more distant countries were added, it would be natural to think that they also could be included in the flat map. You have all seen such maps of the world, e.g. Mercator's projection, and you will remember how Greenland appears enormously exaggerated in size. Now, those who adhered to the flat Earth theory must hold that the flat map gives the true size of Greenland. How then would they explain that travelers in that country reported that the distances were much shorter? They would, I suppose, invent a theory that a demon resided in that country who helped travelers on their way, making the journeys appear much shorter than they really were. No doubt the scientists would preserve their self-respect by using some Greco-Latin polysyllable instead of the word demon, but that must not disguise from us the fact that they were appealing to a deus ex machina. The name demon is rather suitable, however, because he has the impish characteristic that we cannot pin him down to any particular locality. We might equally well start our flat map with its centre in Greenland. Then it would be found that journeys there were quite normal, and that the activities of the demon were disturbing travellers in Europe. We now recognise that the true explanation is that the Earth's surface is curved, and the demoniacal complications appeared because we were forcing the Earth's surface into an inappropriate flat frame which distorts the simplicity of things. What has happened in the case of the Earth has happened also in the case of the world, and a similar revolution of thought is needed. An observer, say at the centre of the Earth, finds that there is a frame of space and time, a flat or Euclidean frame, in which he can locate things happening in his neighbourhood without distorting their natural simplicity. There is no gravitation, no tendency of bodies to fall, so long as the observer confines his observations to his immediate neighbourhood. He extends this frame of space and time to greater distances, and ultimately to the Earth's surface, where he encounters the phenomenon of falling apples. This new phenomenon must be accounted for, so he invents a deus ex machina, which he calls gravitation to, whose activities the disturbance is attributed. But we have seen that we may just as well start with the falling apple. It has a flat frame of space and time into which phenomena in its neighbourhood fit without distortion, and from its point of view, bodies near it do not undergo any acceleration. But when it extends this frame farther afield, the simplicity is lost. And it, too, has to postulate the demon force of gravitation existing in distant parts, and, for example, causing undisturbed objects at the centre of the Earth to fall towards it. As we change from one observer to another, from one flat space-time frame to another, so we have to change the region of activity of this demon. Is not the solution now apparent? The demon is simply the complication which arises when we force the world into a flat Euclidean space-time frame, into which it does not fit without distortion. It does not fit the frame because it is not a Euclidean or flat world. Admit a curvature of the world, and the mysterious disturbance disappears. Einstein has exorcised the demon. Einstein, recognizing that in the phenomena of gravitation he was not dealing with a tug but with a curvature of the world, had to reconsider the law of gravitation. He could not make any possible law of curvature correspond exactly with the previously assumed law of tugging. Thus he was led to propound a new law of gravitation, a law which in most practical cases differs very little from that of Newton, although it has an essentially different foundation. I need not here dwell on the very remarkable way in which Einstein's emendation of the law of gravitation has been confirmed both by the anomalous secular change in the orbit of the planet Mercury and by the observed displacement of the stars near the Sun during the total eclipse of 1919. I might, however, remind you that in the latter observation, the point at issue between Newton's and Einstein's theory was not the existence of a deflection of light rays passing near the Sun, but the amount of the deflection. Einstein predicting twice the deflection possible on the Newtonian theory. The larger deflection was quantitatively confirmed by the eclipse observations. Einstein's main achievement is a new law, not a new explanation, of gravitation. He attributes the gravitation of massive bodies to a curvature of the world in the region surrounding them, and so throws a flood of light on the whole problem. But he is not primarily concerned to explain how material bodies produce, or are associated with, this curvature of the world around them, nor how this curvature is made subject to a law. Although it would be an entire misunderstanding of Einstein's attitude in propounding the general relativity theory to regard it as a search for an explanation of gravitation, nevertheless, I think that the further following up of his ideas has led to a genuine explanation as complete as could be desired. But I am not going to give you the explanation in this lecture. Sometimes an explanation requires a great deal of explaining. I think that we can, without mathematics, form a general idea of why Einstein found it necessary to amend Newton's law of gravitation. Let us return to the illustration of the pig and imagine that we wish to discover the law governing the distribution of fat and lean in the animal. From the breakfast table standpoint, a plausible type of law would be that half of each rasher is fat and the other half lean. And if this turned out to be confirmed very approximately by observation, we might well imagine that we had discovered the exact law of porcine structure. But the case is altered if we give up the breakfast table standpoint and contemplate the animal in a more general way, remembering that he has not been designed with any particular reference to the series of rashers into which our grocer has chosen to slice him. We must now look for a different type of law altogether. Two possibilities may arise. We may find that our proposed law, although expressed in breakfast table parlance, is nevertheless equivalent to a possible biological law. It may be immediately capable of translation into a more general statement which makes no reference to a particular stratification. But on the other hand, it may happen that the suggested law cannot be freed from this reference to a particular system of slicing. In that case, we can only regard it as approximate, perhaps holding fairly well for the slices of which we have most experience, but becoming less and less accurate in the more tortuous parts of the animal. Both these cases are illustrated in Einstein's modifications of classical theory. Newton's law of gravitation explicitly refers to a space-time frame, and therefore to a world stratified into instantaneous states. It proves to be impossible to free it from this reference to a particular stratification without modifying it. In fact, if the crucial astronomical observations had shown that Newton's law, and not Einstein's, was the exact law of gravitation, this would have been evidence of a real stratification of the structure of the world, a stratification revealed by no other phenomena. Einstein's law is the simpler law because it is consistent with what we now know of the general plan of world structure. Newton's law could only be made possible by introducing a novel and specialized feature, a stratified arrangement of structure, which is not revealed in any other phenomena. Maxwell's laws of electromagnetism afford an example of the other type. These, it is true, are stated as relating to the particular slices of the world of events, which are served up to us like rashers instant by instant. But they can be restated without alteration of effect, in a form making no reference to slices. This is a very remarkable property of Maxwell's equations, which was quite unknown at the time they were first put forward. It was brought to light much later by the researches of Larmor and Lorentz. In consequence of this, Einstein is able to take over the whole classical theory of electromagnetism unaltered. He restates it so as to show how it applies generally and is not bound up with the purely terrestrial point of view, but he does not amend the laws. He metes out different treatment to the gravitational laws and electromagnetic laws, because he finds the latter already adapted to his scheme. If I have succeeded in my object, you will have realized that the present revolution of scientific thought follows in natural sequence on the great revolutions at earlier epochs in the history of science. Einstein's special theory of relativity, which explains the indeterminateness of the frame of space and time, crowns the work of Copernicus, who first led us to give up our insistence on a geocentric outlook on nature. Einstein's general theory of relativity, which reveals the curvature or non-Euclidean geometry of space and time, carries forward the rudimentary thought of those earlier astronomers who first contemplated the possibility that their existence lay on something which was not flat. These earlier revolutions are still a source of perplexity in childhood, which we soon outgrow. And a time will come when Einstein's amazing revelations have likewise sunk into the commonplaces of educated thought. To free our thought from the fetters of space and time is an aspiration of the poet and the mystic, viewed somewhat coldly by the scientist who has too good reason to fear the confusion of loose ideas likely to ensue. If others have had a suspicion of the end to be desired, it has been left to Einstein to show the way to rid ourselves of these terrestrial adhesions to thought. And in removing our fetters, he leaves us, not, as might have been feared, vague generalities for the ecstatic contemplation of the mystic, but a precise scheme of world structure to engage the mathematical physicist.